Hi, everyone. Thanks for joining this presentation. My name is Justin Lee. I'm a graduate researcher at Yonsei University, South Korea. This work was conducted in collaboration with Professor Ghang Lee, and it explores how large language models can serve as assistants for structural model review and edit process, independently of traditional predefined software functionalities. So let's begin with a bit of background. In today's structural engineering practice, structural modeling, including model review and editing, are typically carried out within graphical software environments. While these tools are powerful, they require repeated and often time-consuming user interactions. Two main challenges arise. First, the engineers must be proficient with the software's interface and the workflows, something that takes a considerable amount of time to master. Secondly, even with such proficiency, there's no guarantee the built-in functionalities of the software can adequately capture or execute the engineer's intent. So let's take a look at an example task. Suppose we want to change the section of the columns that are supporting third floor office loads to age 300 by 300, but only if they are currently age 100 by 100 sections. This fictitious task could be a mid-design revision task to assign a proper column section to the elements that currently have like a default section assignment, say H100 by 100, which is too small for these types of columns. So the conventional method involves multi-step software interaction. We will look at these steps in more detail in a video demonstration, but it involves multiple conditional filtering, manual selection, then property assignment. As you can imagine, this may require jumping between several menus, several tools, and model views. It's a very high friction process that diverts the engineer's attention away from the actual design efforts and rather into software operations. Now, let's compare that to the proposed method. Instead of going through all the manual steps, we simply describe the task in natural language as a user prompt. This prompt is passed to a large language model. In our case, it's Claude Sonnet 4. The LLM then generates a Python code block tailored to perform this task. This code block is executed on the model data. Now, the result is the same as the conventional method, only now it's handled automatically and without any graphics user interface navigation. Another point I want to make is the project model data is never actually exposed to LLM. Instead, we use a small sample structure to teach the LLM how the data is organized and allowing it to generalize to any project that shares the same format, data format, and which does two things. One, the generate code block is parameterized, meaning it can be saved and reused on other projects. Second, because the actual project data is not exposed to the external cloud LLM service, it provides data security. So this is a flowchart of the inner workings of the proposed system in a little more detail. Most of this coincides with what we have discussed on the previous slide, but an added detail is the prior feedback database you see on near the bottom of the screen. The feedback database is a collection of short, reusable instructions that correct or clarify mistakes made by the LLM in earlier task attempts. These instructions are linked to specific keywords from the user's prompt and are injected back into future LLM inputs when similar tasks are attempted again. Now, this approach turned out to be quite effective in refining the performance of the system, as the error rate quickly dropped as more feedback instructions were collected. In other words, the frequency of requiring user feedback diminished within the domain of model review and edit tasks. So let's actually compare the conventional and proposed methods with the example task. For the conventional method, we start by isolating the relevant part of the model. To do this, first we check the floor load assignments to confirm which areas are designated as office areas. Second, we filter only the areas of interest and the floor of interest for an unobstructed view. Now, as you can see, this can be quite a cumbersome process with many clicks and navigation of menus. Then we check the current section assignment to identify which columns have H100 by 100 sections. Now, once we have all of this done, we can select the target elements or target columns. And once we have that selected, finally, we can assign the new sections, which is the H300 by 300 onto these column elements. With the proposed method, we simply enter the request into the chat. Now, this could be like a typed text chat, or it could very easily be like a voice command. Once we have this chat entered, then like a keyword search is performed on the prior feedback database. Then the generated code is executed, and now we have our sections assigned as requested. And finally, it shows like a summary of what's been done to the model data. To evaluate the proposed method, we first tested three basic task types, which include element filtering, metadata retrieval, and model edit for more granular evaluation. Then we moved on to more challenging and realistic tasks by combining these three basic task types in series into more realistic scenarios, such as the example that we've seen earlier. So for experiment one, where no system prompt nor feedback database was provided, despite the lack of any guidance, Claude Sonnet 4 was able to perform around 26% of the tasks successfully. Now, this is a testament to the non trivial capabilities of the state of the art LLMs, which is quite amazing. For experiment two, only the system prompt with general information such as descriptions of basic element types and geometric context was added. The performance jumps to around 57% in average. Finally, when we have both the system prompt and the user feedback database provided, for the tasks we have tested so far, the proposed system was able to perform all of them successfully. However, an important disclaimer is that we are still in the process of testing these tasks with higher repetition for more statistical rigor. So you will be able to find more reliable results on my next publication on this topic. An interesting result was that the introduction of feedback database improved the combination task category quite significantly, meaning having just system prompt was not enough to perform the combination tasks well. This is explained by the fact that a combination task is a series of basic tasks, meaning failure to perform any of the constituent basic task leads to failure, resulting in poor performance in combination tasks with only the system prompt. Some of the limitations of the proposed system include heavy LLM dependency, limited element types tested, meaning no membranes or wall members were considered. And finally, omission of any type of element generation tests. So now to conclude, we assembled all the necessary LLM communication as a text-based input, which allowed for a simple and straightforward way to leverage a state-of-the-art LLM model without the need for any additional pre-training. We also have validated that a well-crafted system prompt with general instructions, accompanied with more task-specific feedback database instructions, can improve the proposed method significantly. Finally, by only uploading a small sample structure, we not only achieve much faster inference, but also data security of the actual project model. Now, I truly believe this dynamic generation of software features is where AI augmented engineering modeling is headed as LLMs become more and more capable. And hopefully, this study and this presentation has demonstrated a glimpse of what is to come. This concludes my presentation. Thanks everyone for tuning in, and please feel free to reach out for any questions or comments.